Greetings, people. Our next experiment is laser diffraction, where we'll be using a laser source. We'll be using a diffraction grating, and the image that is falling will be made to fall on a screen. Okay, the two words laser diffraction. What do you understand by laser? Laser is a monochromatic source which is having the properties of high intensity. And since it's monochromatic, it is coherent as well, and it is unidirectional. It follows the principle of directionality, and this is the laser that we're going to use. It is a semiconductor laser, and since it's a monochromatic source, the laser will not have the usual property of diffraction, which you see when you pass white light through a prism. It splits into principal, constituent colors. That does not happen with laser because it is a monochromatic source. If you are able to see the dot laser, see? So what we do is we make use of this grating. Okay, you can see that square thing. Yeah, that's called the grating. The grating is actually it's a transparent material which is split into n number of lines which are laser cut by n number of divisions, so that when a point source falls on it, it splits. Okay. So these are the things that are prerequisites for you to come start off with this experiment. Now, what we will be doing here is you have your semiconductor laser and you have the grating mounted on a grating stand. Then you have the screen. Now we need to see to it that the distance between the screen and the grating stand has to be precisely 1 meter. Okay, see, it's exactly at the edge. You have to keep it at the edge exactly like that. Okay, now you just move this grating stand away, then switch on the laser. You can see the dot, right? Yes, no, maybe, yes. Yeah, all of you are able to see it. Now you will not be able to see it. Now, what we need to do is, this is a graph sheet. You have to fold it into 4, okay, in such a way that your foldings fall on one of these lines, okay, and the point of intersection, mark it. Mark it like this, okay. Now what we are supposed to do is, this point has to coincide with this point like this, okay, and you need to see to it that this line, whatever you have, is parallel to the ground. So that will be something like this. Okay, then place your thumb on the tip so that you don't lose track of the tip. Then you may place the grating stand, and now you will be able to see different dots. Maybe that far you may not be able to see, but just mark it. 1, 2, 3, 4, 5, 6 on this side, and do the same thing on this side as well. 1, 2, 3, 4, 5, 6. So that is a total of 6 plus 6, 12, plus the mid node, 13 points. Okay, And these are the points that are required for you to perform this experiment. Then you can turn off the laser source and take the grating. The experiment part of your experiment is done. All you have to do is calculation, for which I have this wonderful graph which is already made. Hope it is visible. So this is how you are supposed to make your graph. I shall send a picture of this later. What you are supposed to do is, I've just drawn the points, whatever we have marked, I've just made it. And what's happening here is, these are the nodes that we marked, okay? And if you see, they are kind of identical. It's like a mirror image. Now what we are supposed to see is, if you have a look at this, each of these form a right angle triangle. A right angle triangle, so we make use of the trigonometric functions. And what we do is, since we are supposed to find the wavelength of the laser source, which is lambda, first we need to find out the value of theta. The angle theta, individual angle theta we are supposed to find. What is the formula to find theta? Theta equals tan inverse xn by L, where L, as I told you, is this length, which is 1 meter. Length L is 1 meter. Keep it in meters only, so that will be 1. That is what I've marked here, 1 meter length. Then you have these nodes. What you're supposed to do is, the markings I've already marked it here, and since you people won't be able to perform the experiment, I advise you to mark it in the same way and start plotting the graph and as well as the calculations. See, what exactly is happening here is, this is the node with the highest intensity, that is called the 0th node. All the other nodes, that is the first node on right side, left side, right side, left side, second node, third, fourth, fifth, sixth. You're supposed to minimum take 6 readings, okay? That 6 nodes is what I've taken. Okay. Excuse me. So, the distance between first node on left hand side, first node on right hand side, what is the distance? That will give you 2xn, where n is the order of diffraction. In this case it is 1, so 2x1. Why it is 2? It's because this side plus this side, total. So it is 2xn. So this will be 2x1, that's what I've marked here. 2x2, 2x3, 2x4, 2x5, 2x6. Those are the different measurements. All are in centimeters, so kindly convert them to meters. That's 10 power minus 2 meters. Okay. Next, what you do is, you're supposed to find the value of xn. You know the value of 2xn. So 2xn divided by 2 gives you xn. Just have a small example which I've made. First reading, I've done it here for you, for your convenience. Do all the other readings as same as this. 2xn divided by 2 gives you xn. So that'll be x1, x2, x3, x4, x5, x6. Okay? Right. Next, theta equals tan inverse xn by L, where L is 1 meter. So we'll find out theta 1, theta 2, theta 3, theta 4, theta 5, theta 6. 6 readings of theta. Substitute each of the theta value in lambda formula. Care has to be taken, people. See here, this, all the readings are in centimeters. So you have to convert it to centimeters and only then proceed. Okay. Since your L is already in meters, it's 1 meter, you need not have to worry much about that. So you'll get 6 readings of theta. Now, once you've calculated the value of theta, what you're supposed to do is, you need to substitute individual values of theta in the lambda formula and find out the value of wavelength. That is, lambda equals d sine theta by n, where n is the order of diffraction. I have written that here. N is the order of diffraction, where n is 1, 2, 3, 4, 5 for different readings. Okay. N1, N2, N3, N4. So it goes on like that. So D, the value of D, it's a constant, it's a grating constant for that particular grating. 48825 times 10 power minus 9 meters is the reading that we have, which is there in your manuals as well. You can use the value as it is. Sine theta. So if you're calculating theta, the first value theta 1, so lambda 1 equals D sine theta 1 by n. N is 1, so it will be by 1. Similarly, if I'm finding the value of lambda 6 will be equal to D sine lambda 6 by 6. Okay. Why 6 is because it is by n. N happens to be the order of diffraction, and for the sixth case, it is 6. Right? Right. So you will get 6 different values of theta. Take the average. That will be lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, lambda 6. 6 different readings of lambda you will get. So how do you take the average? Lambda 1 plus lambda 2 plus lambda 3 plus lambda 4 plus lambda 5 plus lambda 6 within bracket whole divided by 6. That gives you the average. When you're substituting this in your calculator, kindly open parenthesis, lambda 1 plus lambda 2 plus lambda 3 plus lambda 4 plus lambda 5 plus lambda 6, close parenthesis, divide by 6. Otherwise, what will happen? Only the last reading divided by 6, everything else will be added, and that will give you wrong result, which we don't want. Clear? So that completes your laser diffraction. To just make the things more clear, I'll just show this